Welcome to the iSystem webinar AUTOSAR Classic Timing Analysis. So my name is Errol, I'm the moderator. So I'm the guy taking your questions during the webinar, and Felix, currently located in the US, will do the presentation. Felix is systems engineer and with a lot of experience in terms of timing analysis, especially with AUTOSAR Classic. And I think that's the best fit for today.
Okay, thank you, Errol. Thank you very much for the introduction. Yeah, good morning to the people in the US and good afternoon to everybody in Europe. Thanks for joining us today. So this is my regular business self, and right now I'm looking like that, except my hair is a little bit longer maybe, and I'm trying to stay healthy. So I hope you guys are all staying healthy too. So let's have a look at what we're going to do today. So this webinar is about timing analysis, and specifically in the context of the AUTOSAR Classic operating system. So we will try to understand how hardware tracing can be utilized to understand the behavior of AUTOSAR-based real-time applications, and then hopefully we can understand the timing behavior of our applications, and then we can also optimize it and improve it. So with that being said, I will start with explaining the challenge, like why would we even want to do this type of real-time analysis. I will talk about different classes of real-time analysis, and then we will have a look at tracing and hardware tracing in particular, and how we can utilize it to gather the data that we want to get. And then finally, I will explain how all that comes together and hopefully solve the initial challenge that we set up to solve. So let me start with the following situation. You are getting up in the morning, going to the office, or right now into your home office, you got your coffee ready, you're really motivated to work, you have got some embedded development to do, really excited, some fancy algorithms or whatnot. So you get your debugger ready, you're ready to run the application on your target, and in general, you're really happy, right? That's what it's all about, solving challenges, making embedded software great. And then this happens. WinIDEA is not responding, or some other program is not responding, and you're getting all sad and not able to do what you set out to do. So what do? Usually, if something like that happens, you're probably gonna go ahead first and open your task manager and investigate what's going on, and then you might see, oh my god, like Windows is doing updates again, or like my virus scanner is taking way too much load, and that's why WinIDEA is not able to work. So we'll just get rid of those. You don't need all those distractions, and you just go ahead and start working in WinIDEA. So maybe you're familiar with that situation. So you kill those tasks, and then you're finally happy. Your CPU can now do what you wanted to do, and you can start working productively. So now, you may or may not think this was funny, but you may be wondering, like, why is this important for embedded systems? And the thing is, this type of behavior that you can observe on your desktop computer, this can also happen in embedded applications. So what we can see here is a screenshot from WinIDEA. This is the so-called profiler timeline, and it shows us what tasks our application is executing over time. So this light red color here indicates that the task has gone into the new state, and then it's waiting to be scheduled, and then eventually here it goes to the running state. So it's actually executed on the CPU core, it's preempted, and then executed again, and it finally goes into the suspended state. So the clever guys and girls might notice something here. So up here we have a timeline, and you can say in the name, and this is actually from a real world project, I just changed the task name here to not give away any information, any confidential information, but I indicated that this is supposed to be a 10 millisecond task. But if you look up into the timeline view here, you can see that the task is activated here, but then it's actually not executed for another 40 milliseconds. So there should be a couple of other activations here every 10 milliseconds, but it's not actually executed. So the same type of behavior that happened on your desktop computer where WinID did not get enough scheduling time and crashed, this can also be in embedded applications. And if we fail to notice those issues, then the consequences are much more severe compared to a desktop computer, right? There are real lives at risk if, like, my automatic braking system doesn't break because there's some issue like this where a task is not executed as often as it should. So this is really the issue that we are trying to hand manage with timing analysis. Okay, so this is the reason why we're doing all this work, and this is the motivation for the following slides. So let's have a look here at WinID again. So we agree, hopefully at this point, that timing in embedded applications is important, and that's why we have the WinID analyzer. That gives you the possibility to record trace data, to have a look at the dynamic behavior of the application, and also to calculate statistics. So this is the raw trace data that we are recording from the target, and then we can visualize it in the profiler timeline view where we can see which tasks and which ISRs are being executed over time. We can also see the runnables and function potentially. We can calculate statistics for those tasks and functions. And then the WinID analyzer can also do code coverage analysis, which is another really important safety-related feature, but not so much in the context of this presentation. So we are mainly focusing on the timing part here. So if we agree this is what we want to have, let's dig a little bit deeper and discuss what timing analysis is all about and how it works in a little bit more detail. So on this slide, I have a hierarchy of timing analysis techniques. So you kind of read the slide from the inside to the outside. Like, this is a class, this is a class, this is a class, and the outer classes include the features of the inner classes. So if you start analyzing the timing behavior of your application, you might have an idea like the following. Well, I want to get an idea about like which functions and which tasks and which ISRs are running for how long in my application over the duration of my observation. So what I could do is I could do a sampling in the simplest case. So sampling would mean you use your debugger to read out the program counter or to read out a running task or running ISR variable periodically. And so whenever you read out that running task, running ISR variable, you know which task an ISR or ISR is currently running. And then you can use that data to calculate a quantitative CPU utilization. And you could do the same for the program counter, and then you would get the information about which functions are executed for what percentage of the time. So that's the simplest thing you could do. And the nice thing about that is it's simple to set up. It doesn't take any special hardware besides your debug system that you have anyway. But what happens if you actually realize, oh, a certain task takes much more CPU load than I expected? The problem then with sampling is that you don't get any deeper insight and in like why this violation has occurred, okay? So that's sampling. Then if you want to get a little bit more sophisticated than that, the next step would be to calculate statistics. So that means you would maybe add some instrumentation to your software, let's say at points where runnables or tasks are started to be executed and stopped. And then you would read out a counter at that point and calculate the difference. And then you would get certain metrics like the cross and the net execution times of your tasks, ISRs, runnables. And the cool thing about that approach would be, firstly, it's probably more precise than sampling, depending on how you implement it. And secondly, you could also remember kind of the min, max, and calculate the average metrics. So you would get a more detailed picture of the timing behavior. However, you still have the problem if you actually detect that, let's say, a task has a higher response time than it should have. You are able to detect that there's an issue. You would be able to detect that your task gets not activated often enough, as shown on that initial example, but you wouldn't be able to find out why exactly did that happen. Even with the statistics, you are not really able to get that information easily. So that brings us to the final class in real-time analysis, and that's the timeline view. And the timeline means really that you have a stream of events. Like an event could be a task gets activated, a task gets started, a runnable gets started, runnable gets terminated, task terminates, and ISR starts, and so on. So you have a series of events, and with each of the events, you have a precise timestamp. And because you have that timestamps, you can calculate all those metrics that are part of the lower classes. So you can calculate all those metrics, and then if you detect a violation of a metrics, you can actually jump into the timeline and find out why exactly that violation has happened. So maybe there was an ISR that you didn't anticipate, or the task was waiting for a certain resource like a spin lock that was not anticipated. So you can really jump into the trace and understand what's going on. In addition to that, you can do a wide range of other analysis techniques. You can validate requirements and see like how many of them are violated and fulfilled. You can calculate the CPU utilization for the whole trace, but also over time, like so for certain time slices. You can do a event chain analysis, which is a big topic in AUTOSAR, and you really get the full insight into the behavior of the application. So the timeline view is really what you want to get if you want to do real-time analysis properly. So the question then is, how do we get this timeline? So we agree like having all these events is really beneficial, but how do we get them? So this is where tracing comes into play. Tracing means exactly recording events from the CPU and then analyzing them. We call that profiling. So it's tracing, recording the data, and then profiling, analyzing the data. So historically, there's three main trace techniques. Software trace spacing works by adding instrumentation to the code to generate messages. Those messages are buffered in memory and then sent off chip, for example, via a network interface like CAN or Ethernet, or they could also be read out by the debugger. In contrast to that, hardware tracing works by utilizing a dedicated on-chip trace logic. So that means there's a dedicated part on the silicon that is capable of generating trace messages, and then it sends that trace messages off chip via a dedicated trace interface. So the difference between those two is significant, of course. For software tracing, you don't need any special hardware. You just need your microcontroller that you already have and the network interfaces that you probably already have. And then you add instrumentation and you can record trace data. Of course, the problem with instrumentation is it generates an overhead, potentially a significant overhead. Also, since the messages are buffered in memory, you have only a limited number of objects that you can record, and usually also have only a limited trace duration. So you add an overhead. If your CPU load is already really high, that overhead might even kill your application completely. And the number of trace objects and the trace duration is limited. In contrast to that, with hardware tracing, you don't need instrumentation. It's all done by the on-chip trace logic. So that logic actually doesn't interfere with the behavior of your application. So you create no overhead at all. The application behaves exactly the same as it would when you wouldn't use hardware tracing. You can record a higher number of trace objects, and you can record much longer. So this is like all fairly relative, like one means high number of trace objects. High number of trace objects, by that I mean it's usually feasible to record all tasks and ISRs, and often it's also feasible to record even runnables and functions in addition to that, whereas runnables, like recording 200 runnables with software traces, is definitely a challenge, usually not feasible. And long trace durations here means could be seconds, but we can actually go up to minutes, and yeah, like minutes, multiple minutes. So we have customers that we record even for, let's say, 10 minutes and longer. So that's definitely feasible with hardware tracing, and that definitely wouldn't be feasible with software tracing. Of course, with hardware tracing, you need dedicated software. You need the on-chip trace logic, and you need the debugger to interface with that trace logic to use the dedicated trace interface. So this should make clear the difference between software and hardware tracing. And now it gets a little bit tricky. There's also what's called hybrid tracing. So hybrid tracing is really a combination of the two. So why would we want to do hybrid tracing? Well, for example, there are certain microcontroller architectures that don't have full hardware trace capabilities, that don't have full program and data trace, and we will talk about what that means in a second. But they don't have the full hardware trace capability, but they might have a compromise. So they might have something like on the RH850 that's called software trace. And the way that works is you execute a dedicated instruction, and when you execute that instruction, like you have to add a little bit of instrumentation to execute that instruction, but then for that instruction a hardware trace message is generated, right? So it's a compromise between software and hardware tracing, and that can come in all, like that can be more skewed towards software tracing, or it can also be closer to pure hardware tracing. I just want to say anything that is a combination of the two is considered hybrid tracing, and then comes with the advantages of hardware tracing, but also with the disadvantages of the two. So depending on the project, whether one has to decide on a case per case basis if hybrid tracing is a feasible approach. So if that was confusing, let's zoom one level further in and like just focus on hardware tracing, and then try to make that really clear. So hardware tracing, as I said, works by using a dedicated area on the silicon. So you have a dedicated trace logic. So this block diagram shows our target processor, then the blue box and the PC with WinID where we analyze the data, and the orange block is the CPU core. So that's where your application is executed, and then this program trace logic, data trace logic, and instrumentation trace logic, that's the hardware trace unit. So those three units are connected to the CPU core and can observe what's going on. If those blocks detect events that are of interest, a trace message is generated, a timestamp is added, the data is buffered somewhere, and then sent off chip via this dedicated trace interface. On some architectures, the timestamp is actually not added on the chip, but on the blue box, so that's why it says timestamp. So it's either timestamp generation might be here on the target or here inside the blue box. There's another buffer, and then the data is sent off to the PC, where we can do all this fancy analysis that we saw on the previous slides. So this is how the trace process works. And then you can see there's three different trace blocks here. The first one is program trace. So in general, hardware tracing can be further separated into program flow trace, data trace, and instrumentation trace. Program flow trace can be thought of as recording the program counter. So you really get the full information, like which instructions is the processor, the microcontroller executing. So you can see when a function is started, when a particular branch inside the application is executed, when a function returns, and so on. So you really get full insight into the runtime behavior on the function level of your application. The challenge with program flow trace is that it generates large amounts of data. So usually it's not feasible to record long program flow traces, except if you're using a high-speed trace interface. Then the next main technique, and for that kind of analysis that we want to do, the most important one is data tracing. Data tracing means you record write and read accesses to dedicated areas of the memory. So you could have a dedicated variable, or let's say a running task or running ISR variable, for example, and you can configure the data trace logic to record all accesses to those variables. So whenever my variable is written, I get a message with the address of that variable, the value that was written, and the timestamp. And then I can use that for the timing analysis. So that's data tracing. And then finally, instrumentation trace logic is actually a hybrid technique. And I mentioned software trace earlier, like software trace would be the example for RH850. And then there are other techniques for other microcontrollers. But the way that works is you either execute a dedicated instructions or you write into a dedicated memory area in software. So you have to do that via instrumentation, hence the name. And then for those instructions, a trace message is generated. So it's a compromise between pure instrumentation and data trace. So that's what this instrumentation trace logic is about. Okay, so this is the foundation. Like these are the techniques we have available to gather the data that we're interested in. So now the question is, what do we actually want to record? So let's go back. What were we actually interested in? We want to see the tasks. We want to see the interrupt service routines, but then we also want to look further into the RTE and potentially analyze runnables, RTE communication, or we might even zoom in further and see particular functions that are of interest for our analysis. So the question is, how can we use hardware tracing to get these informations? And the first step is the so-called ORTI file. So ORTI stands for OSAC runtime interface, and OSAC is the standard that came before AUTOSAR. So all your AUTOSAR operating systems still create a ORTI file. So if you generate the OS, then an ORTI file can also be generated. And that ORTI file contains information about how to trace tasks and how to trace ISRs, alarms, and other OS objects. So by providing that ORTI file to WinIDEA, we can configure a trace so that we can record task states and the currently active ISR. If we want to go beyond that, if we want to record RTE objects like runnables, the ORTI is not sufficient because when OSAC was created, the RTE didn't exist yet, right? The RTE was invented by AUTOSAR, so ORTI is not aware of the RTE, which is why we created a so-called iSystem Profiler XML file, which extends ORTI. So ORTI supports OS objects, but the profile XML extends it so that RTE objects and also other features are also supported in addition to that. Finally, there's also in AUTOSAR, in the AUTOSAR RTE, there's also the possibility to add so-called timing hooks or virtual function bus trace hooks. So we can utilize those hooks for the OS and for the RTE to potentially add instrumentation if you want to use a hybrid trace approach and gather the information about runnables, tasks, and ISRs. So those are the things that those are the sources that we can use to identify the objects that we want to trace. I know I'm a little bit vague here because if we actually would look at a particular use case, it depends a little bit which approach is the best. So I just want to give a general overview here, and then we would have to decide on a case-by-case basis which is the best approach. Okay, so let's put this all together. So if you're confused by the previous slide, this should hopefully make it a little bit clearer. So we talked about trace techniques. It's here on the left side. We have program flow trace, data trace, could use data trace with a little bit of instrumentation. And then there's instrumentation trace. Okay, so those are the trace techniques we have available. And then on the right side, we have all those objects that we might potentially be interested in. So the simplest case, the hello world of operating system profiling, as I like to call it, is running task and running ISR profiling. Then, if we want to go be a little bit better than that, we could not only trace the currently running task, but also the task states. So that gives us a little bit more information. Then we mentioned runnables, and then there could be other objects like RTE communication or semaphores that we might want to record. And then now this matrix shows us which trace technique can be used for which for which trace object. So, for example, if we want to record the currently running task and currently running ISR, that's a simple variable that we can record via data tracing, and that's supported by the RTE file. If we don't have data tracing available, then we would have to use timing hooks to instrument the application so that the running task and the running ISR is signaled, and then that way we would use instrumentation trace, and that would work via the iSystem Profiler XML. And then I don't want to explain the full diagram in detail, but you can kind of, depending on the trace technique that you have available and depending on what you want to record, you can use different approaches via instrumentation. Sometimes the RTE file is enough. Sometimes you need an iSystem Profiler XML file. So that's how it comes all together. And then because there are so many different combinations, it's important that we help you to understand like which use case is actually feasible for you. And that's why we have the 3 pillars of AUTOSAR profiling. So on our webpage, you can find a list of application notes for the different operating systems and for the different microcontrollers that explain which trace capabilities are available and which trace technique is the most efficient one for your use case. So that's the first pillar. Then secondly, depending on the trace approach you choose, you might have to create instrumentation, you might need a profile XML file, you might have to use so-called Vinetier profile inspectors. So in order for you to not have to create all those files manually, we provide a so-called itchy script, iSystem trace configuration helper. And we provide this itchy script, and it helps you with generating those files so you don't have to do it manually. And then finally, since there are so many combinations, it's usually necessary, or we are able to help you like finding a proper solution. So we provide consulting. So if you have a particular microcontroller operating system combination, and if you're not completely sure if OS profiling or RTE profiling is supported, then we can help you. You can contact one of our FAEs or system engineers, and then we will guide you through the whole setup of WinIDEA and generating all those files that are necessary. So those are the 3 pillars of AUTOSAR profiling. And again, the main message here is we have a couple of resources, but if you do online, if you're not able to figure it out by yourself, you can contact us and we will be glad to help you. So finally, if you put all this together and you set up OS profiling in one way or another, either by yourself or with our help, then the final picture will look like this. So this is again the WinIDEA profiler timeline. And then you will be able to see the runnables and functions that are being executed over time. You will be able to see the different tasks that are being executed together with their states. So we'll see when a task is activated, when it's running, and when it's waiting. You really get the full insight into the behavior of the operating system. You see the ISRs. And then based on that information, you can really calculate all the metrics and analyze the full behavior of your application, like all the things that we have mentioned previously. So let's go back to our initial example. So we mentioned we had this 10 millisecond task, but it was actually only activated, let's say, about every 50 milliseconds. So we were able to detect that issue, and potentially we would have been able to detect that issue too with other techniques, for example, with statistics. But how does the trace actually help us to resolve such a problem? And now, if we look at the rest of the trace data, and of course there are a couple of other tasks, you can see that there's another 5 millisecond communication task. And if you look at the timeline up here, and if you look into at the name of the task, it's supposed to be executed every 5 milliseconds. But if you look at the time scale here and how often the task goes into the new state, like that's the task when it gets freshly activated, we can see that the period is much higher than 5 milliseconds. Looks like it's every 1 millisecond. And in this case, that was actually the issue. There was some silly misconfiguration going on where this 5 millisecond task was executed 5 times as often as it was supposed to be. And then that generated a whole a whole bunch of additional load on the target system, and that led to the 10 millisecond task being delayed and not being executed as often as it should be. So then once that was clear, it was easy to move the 5 millisecond task into its defined raster, and the timing issue could be resolved. So that's a real world example that shows how this profiler timeline data can be useful to optimize the behavior of the application. All right, and then actually concludes the main part of the presentation. So I just want to point you to some further resources here. On our homepage, we have online training. So we have kind of beginner tutorials that go through common use cases. So here it shows test idea and win idea, but in the meantime, we actually have getting started with tracing that explains the basics of hardware tracing. And we will actually do another webinar that will be more basic and will explain the beginner, or will explain tracing in a beginner-friendly way, and also talk about how to configure different architectures, how to tackle certain use cases. So we have those trainings available on our homepage. And then I don't have a link here, but then we also have the application notes on our homepage. So if you go to isystem.com, scroll down to the sitemap, you can find a section called application notes, and that's where the tracing and OS profiling for different operating systems is explained. And with that, I say thank you for your attention, and then we can ask Errol if there are any questions.
Sure. Thank you, Felix, for the presentation. We had a couple of questions. One was about time stamping. When you showed the architectural slide, how trace works, how the trace works, it was a AURIX dedicated question. So the question is how the timestamp generation is done. Is it done on the target using an AURIX or on the blue box?
Yeah, that's a really good question. On the AURIX, it's actually done on the target, and there are actually different techniques for generating the timestamps, and I don't want to go into too much detail, but the AURIX has a so-called incremental timestamp called ticks, and those are actually cycle accurate. So yeah, timestamp generation is done on the target. They're dedicated trace messages with the timestamps, and then those can be used to reconstruct the timestamps for the actual data and program flow trace messages on a cycle accurate way, or half cycle accurate actually. Mm-hmm.
Okay. Another question was you mentioned iSystem XML proprietary format to get more information about OS objects. Is there a standard? I mean, we didn't mention RTE. There is a standardization process. Could you say a couple of words to that?
Sure. Yeah. So I just want to make this clear why this iSystem profile XML is required, and then we can talk about RTE. So again, the challenge with RTE is that it was invented and designed before AUTOSAR even existed, right? So that's why certain objects are not part of the RTE file, which is why we invented this iSystem proprietary format called Profiling XML, and then that solves some of the issues with regards to RTE awareness. Of course, it's not. This is not like a permanent or ideal solution. Ideally, AUTOSAR or the RTE standard, the RTE file would be extended so that it already includes the information about AUTOSAR runnables, AUTOSAR RTE communication. And that's what this RTE standard that Errol has just mentioned is about. So RTE stands for AUTOSAR Runtime Interface. So that's a work group that is currently operating within the AUTOSAR standard and working on the successor of RTE, and it is already released to a certain degree, but it's not yet at a state mature enough to support all those use cases as well as the Profiler XML. So yeah, the short answer is like we are working on standardizing this support for RTE objects, but it's not there yet. So that's why we have this iSystem Profiler XML to provide our customers with a solution in the meantime.
Mm-hmm. Thank you. Another question is, how can we measure the load of the OS itself? Context switching interrupts and so forth.
Yeah, so that's a good question. So if you have set up the OS profiling, you will have this view here, right? You will, for each of the cores, you will see all the tasks and when they are running. So whenever a task is in the dark red state, it's allocated to the core. It's currently being executed by the CPU. So to calculate the load for a particular task, what you do is WinIDEA gives you statistics for each of the objects here. So for example, you can either do a right click here on the task and do properties, or there's also a dedicated statistics view. Showed it on the initial slide. Maybe I will quickly go there and show it again. People say you shouldn't go back and forth, but that's okay. We'll just violate it. So let's have a look at the slide here. So you can see we have this dedicated statistics view. And then WinIDEA shows you for how long was a task actually executed on the CPU core, like that's the net execution time. For how long was it preempted by another task or by ISR? How often was it executed, and so on. So there's a bunch of different statistics. So if you are interested in the CPU load, what you do is you take the net execution time for a particular task, like how long it was executed, and you divide that by the total duration of your trace recording. So in this case, you can see this task A was executed for 2.7 seconds. The whole trace was 6.26 seconds. So by dividing those two numbers, you get that this task causes a CPU load of about 43%. If you want to get the load for the CPU as a whole, you can either add up all the task loads, and of course you also have to include the ISRs, or sometimes, or like not sometimes, actually most operating systems, most AUTOSAR classic operating systems have a so-called idle task. So if you have an idle task, in this case it's called no task, but it could also be called core zero idle task or core zero background task, you can calculate the load. You can use WinIDEA to calculate the load of that background task, and then the 100% minus the load of the background task is then the actual load of the application. So those are the two approaches. Either you sum up all the task and ISR loads, and then you get the load in that way, or you simply look at the idle task and then take the value 100% minus the idle task. So that's how you get the CPU utilization of your application.
Yeah, thank you. Lots of other questions. Maybe we take another two. The Itchy Python script generator, is this something that is part of our distribution within the product, or how can I get this one?
So that's also a really good question. So right now, we actually ship Itchy on a case-to-case basis, and it actually the demand is quite high. So right now, the process is still like you contact one of our system engineers, for example, me, and then I will help you set up this with this Itchy script. But we are currently working on making Itchy into a properly tested, regression tested, executable that will be delivered with WinIdea. So that's going to be released within the next, let's say, 2 to 3 months max, I would say. So right now, the process is you have to contact your FAE, and we will provide you with that script manually. And then soon, hopefully, it will be a part with WinIdea. And actually, when you download WinIdea from our homepage, this Itchy script will already be included. Yeah, but good question.
Then also a question related to tracing in general. So if my PCB has no trace port available, just basic JTAG, yeah, what are the possibilities and limitations in this case?
Yeah, that's a really good question. So there are different solutions, and it all depends on the microcontroller that you're using. In general, if you have only a JTAG interface available, there are two cases. So the first case is that you are using a microcontroller that has a so-called OCTB, an on-chip trace buffer. So if you have an on-chip trace buffer, then what you can do is you can record a trace into that on-chip trace buffer till the buffer is full, and then you can read out the data via the JTAG interface and analyze it. The problem with the on-chip trace buffer is it's usually rather small, relatively speaking, so you won't be able to record a trace for a long time. If you're only recording running task and running ISR, you might still get like a couple of milliseconds, but it's definitely not in the seconds range as I claimed earlier. So that's one approach. If you have the on-chip trace buffer, if you don't have an on-chip trace buffer and you have the JTAG interface, there's no way to do like a pure hardware trace. So instead, what you need is a so-called like a streaming interface, like Nexus, for example. And if you don't have that on your PCB, the solution is usually to use a so-called emulation adapter. That means you replace the microcontroller on your target with a soldering unit, and then you put the emulation adapter onto the soldering unit, and that emulation adapter has a microcontroller that emulates the microcontroller that was previously on your PCB, but it also makes the serial trace interface like Nexus, for example, available. And then that would be a way to get trace data while still having the same behavior of the application as before, even if you don't have the serial trace interface available on your PCB. So, but again, it all depends on the microcontroller. But so if you want to go get more specific, it's best to contact us. But that's usually the solutions that are available. If you don't have the trace interface and you don't want to change your PCB, emulation adapter is usually the recommended solution. On some other architectures, I just want to mention it for completeness sake. For example, on the RH850, there is a so-called instrumentation trace logic. So that's the RH850 software trace, and then that actually uses one of the pins of the JTAG interface. It's a dedicated protocol called LPT4, and then that would be would allow you to stream data off chip even if you just have a JTAG interface. But again, it's highly microcontroller specific. So depending on what you're using, there may or may not be an elegant solution.
So thank you for attending, and hope to see you soon again here.
Thank you. Bye-bye.